So looking at relative velocity. Oop, and I forgot to plug in my speakers here. Let's do that. Sorry for the noise. Let's suppose you're traveling. We're going to start out with freeway because you've all been in cars. Let's suppose you're traveling down the freeway at 100 kilometers an hour. When a white Honda Escort goes zipping by you. Honda Escort? Ford Escort, right? Yeah, whatever. White Escort hurtles by you, blue smoke and all, at 140 kilometers per hour. You don't see that the Escort is traveling at 140 kilometers per hour because you're already moving. Compared to, actually, relative to, which really means compared to, relative to you, how fast is the Escort moving? If you're traveling 100 kilometers an hour forwards and the Escort's traveling 140 kilometers an hour forwards, how fast do you see it moving? Brad? 40. We call that relative velocity. We say, if you want to, you can imagine that you're standing still, that you're the center of the universe, and you can say, relative to me, what do I see? What does it appear to me? Now, someone standing on the side of the road, relative to them, they'll see you traveling at 100 and the Escort traveling at 140, but relative to you, you can say, you know what, I'm standing still. And the Escort's retreating, going away from me at 40 kilometers an hour. That's its relative velocity. Do you see how we got the 40 from the 100 and the 140? It's going to be some subtracting. Okay? The relative velocity of any object moving depends on your point of view or your frame of reference. Sure, you see the car moving away at 40 kilometers per hour. Hey, what does the driver of that car see you doing? Traveling backwards at 40 kilometers per hour. Relative to the Escort, because when this driver looks in the rearview mirror, he sees you moving away from him. Right? Got to use your imagination a little bit here. Yeah? So, another example. A zebra is running away at 50 kilometers an hour from a cheetah going at 90 kilometers per hour. What velocity does the zebra see the cheetah as having? And vice versa. So from the zebra's point of view, relative velocity of the cheetah, V relative is 90 minus 50. The zebra sees the cheetah gaining on him, traveling forwards at 40 kilometers per hour. The zebra, when it turns its head, says, uh-oh, and it sees it moving forwards towards him at 40 kilometers per hour. What does the cheetah see? The cheetah, looking straight ahead, feels like it's reeling the zebra in. It feels like the zebra, it imagines, it looks to it like the zebra is retreating backwards at 40 kilometers an hour, and it's hopefully going to get it to lunch. Is that okay, Alex? Yeah? All right. So, if the zebra starts out 90 meters ahead, how long will it take until the cheetah catches up? Here's our first question. What are they asking me to find? I guess okay. Now this year for relative velocity, and Grant, I'm so glad you asked the question you did earlier about the homework. This year for relative velocity, we're going to always have no acceleration. We're not going to include a relative acceleration. By the way, what is the relative velocity? So I'm not going to use the 90 or the 50. What am I going to use for my velocity? 40 what units? Okay, we need to do a conversion here. How do I go to meters per second from kilometers per hour? Do you remember? It's something to do with the 3.6. Times by 3.6 or divide by 3.6? How many meters per second is that? Is it 11.111111? Okay. So I'll go 11.1 meters per second, but I'll keep that 11.1111 on my calculator and use that as on my answer button. Hey, I'm looking for an equation that has d, t, a, and v in it. I'll give you a hint. Grant, it's the same one that we pulled out for the sound question that you did earlier. Which one was it? Do you remember? Okay, it's going to be d equals v relative t plus a half a t squared. But since there's no acceleration, Jake, it really just ends up being d equals vt. In fact, this is the one that you did in Science 10 last year all the time when acceleration was a scary thing. This is why I hated the Science 10 part. It was, with no acceleration, this is boring. You can't do free fall. Hey, what are we trying to find? Hey, how did we get the time by itself from this? Okay. Time is going to be d divided by v. It's going to be 90 divided by 11.1. .1 seconds. Let's really divided by answer button. I should have gone a little more accurate. Let's go, is it still 8.1? Yeah. Oh yeah, almost exactly. It probably, for you guys that use the answer button, it's exactly 8.1 seconds, is it? Yeah. Okay. Hey, what this means, by the way, is if safety for the zebra is 8 seconds or less away, then Jake, the zebra lives. If safety for the zebra is more than 8 seconds away, more than 8.1 seconds away, the cheetah eats. This is the great circle of life, Simba, the great circle of life, right? So if we have two objects, both of which are moving, we don't use their speeds. We use their relative speeds. Example 2 says, state the relative speed in each case. So we have one object traveling at 40 kilometers per hour to the right, another object traveling at 40 kilometers per hour to the right. What's their relative speed? Relative to each other, what's their speed? 0. They both, as far as they're concerned, see each other standing still and the world moving around them. Right? What about this second situation here? If this left object is traveling to the right at 40 kilometers per hour and the right-hand object is traveling at 20 kilometers per hour, what's the relative speed between them? Now, it's going to depend who I'm talking about. Let's say this guy, sorry, let's say the front guy, he sees this guy gaining on him at 20 kilometers per hour. The left-hand car sees this guy traveling backwards towards him at 20 kilometers per hour because he's reeling him in. Right? Hey, what about if they're facing each other? What's the relative speed of each other? Think about it. 60. 60. So what kind of questions can we do? Oh, something like this. Example 2. How long does it take these trains to completely pass each other? So I guess the top train is 150 meters long and it's traveling at 13 meters per second. The bottom train is 100 meters long and it's traveling at 5 meters per second. Well, this would be tough if I tried analyzing each of these separately, but the solution is going to be to actually just look at their relative velocity and figure out how far the back train has to travel to catch up. I'll show you what I mean. So I would argue to catch up to and pass the front train, the back corner has to eventually get level with the front of the front train. You okay with that? That's what passing means? Okay. What distance is that back corner going to have to cover in order for it to get to the front of the front corner of the front train?
215 meters.
Ah. Right? Oh, and what's the relative velocity between these two trains? let's say the back train is traveling forwards at 8 meters per second. I've told you that for relative velocity, there's not going to be an acceleration. We're going to keep it straightforward. Although it wouldn't be that tough to add one in. Nah, physics 12. What are they asking me to find? How long? Okay. I'm looking for an equation that has D, V, A, and T in it. Yeah. In fact, the same one as we just did. In fact, you're going to end up with this. D equals Vt, where the V is the relative velocity. What happened to the half AT squared? Well, yeah, A is 0. What happened to the VI? Well, it's V relative. We're modifying stuff. Okay. Oh, Brad, how would I get the T by itself? Remember how tough this used to be? Yeah? Yeah. Divide by what? Because I think you're right, but divide by?
T.
I want to get the T by it. I want it to stay, so divide by V, right? So it looks like it's going to be 250 divided by 8. My units match. I'm in meters and meters per second. Okay. I'm going to give you a question similar to this on your test, but I think because it's going to be a car question, I'll probably give you the speeds in kilometers per hour. In fact, I think on your test, that'll be the only time I give you a speed in kilometers per hour, but I should do that at least once, so just to remind you that unit conversions are handy. Although I kind of wish speedometers were meters per second, and we could, oh, whatever. That would scare people. 200 divided by 8. 31.25. I'll write that down for now. 31.25 seconds. How many sig figs? It looks like, well, how many sig figs in all my data here? 3. I guess if I was being really, really fussy, 31.3 seconds. Hey, what if they're heading towards each other? Example 3. But before you turn the page, by the way, so how long does it take the big train to pass the little train? How far do they travel in total for that to occur? Well, now I've got the time. How fast is the big train really traveling? 13. You know what? It's going to take 406.25. This is going to happen because in real life, they aren't stopped relative to each other. They are both moving forwards, yes? So this would happen over 406.25 meters. That's how far both of them would travel for that back train to pass the front train. Yeah? So other stuff you can ask. Anyways, example 3. How long does it take for these two trains to completely pass each other? Same question, except now we're heading towards each other. Okay. I guess to completely pass the back corner here has to pass the back corner there. That, to me, is the definition of passed. Yeah? Okay. So looking at that, what's the distance that we have to travel in order to pass each other relative to each other? Well, let's see. This back corner has to travel that far. How far is that? Then it has to travel that far. How far is that? Then it has to travel that far. Oh, you know what? How far does that back corner have to travel before it gets to the back corner of the other train? Change colors, Mr. Duke. 120 and 260 and 80, right? Which is what? 460 or 460? Okay. Oh, again, they're asking us to find time. Again, for a relative velocity question, I'm not going to give you an acceleration. Our speeds are going to be constant, Josh. Oh. What is the relative velocity? 16. And again, Olivia, what we're really doing is just using our imagination. We're pretending, hey, suppose this train was just standing still and this one was moving at 16 meters per second. That's a much easier question to try and solve. Brad is saying, hey, Duick, it's going to be this again. What happened to the half AT squared, Jake? Okay, good. Hey, Jake, my friend, how would I get the t by itself? I would totally do that. So you're saying it's going to be 460 divided by 16, and here's hoping my answer that I wrote here is correct. Tell me I get 28.8. 28.8. 28.75, but I'm looking at my data. I guess 3 sig figs. 28.8 seconds. By the way, if a police officer is driving in their vehicle and they see a speeder and they point their radar gun at the speeder, the radar gun has to do a relative velocity calculation because the speeder, compared to the radar gun, might only be going 50 kilometers per hour. But if the police officer is going 100 kilometers per hour on the freeway and the radar gun measures 50, how fast is the speeder actually going? 150, but the radar gun does that calculate, takes that into account. So the police officer doesn't have to do the math, doesn't have to look at a speedometer and add it. The radar gun would say 150, that's a speeder. Okay. I like to try and give my students an idea of what's fast and what's not. I try and make my questions up somewhat realistically. So you're going to find, as I introduce new concepts to you, often I'll say, let's talk about what a really big and a really big small is of this example. So let's talk speeds. So I wrote mix and match speeds. I listed a bunch of speeds, or a bunch of examples, and then I wrote a bunch of speeds. Is that someone's phone back there? Whose phone was that? So, Timbits, please. Take your phone out, put it on vibrate, but on your calendar, can you put that we would like some Timbits next class? Actually, is Chris doing next class?
Yeah, I'll do
So Chris is going to be doing Monday. Can you put for next week? Oh, Wednesday, the day of the test. Could you bring us some Timbits, please? Yeah, I'm gonna get my one out of him. We'll get him. Jordan knows us too?
No, it's just funny. Like I heard like a little boy say, he owes us.
Oh yeah. By the way, again, and I've told you, this is a classroom rule I've never had to enforce. The mob has always enforced this rule for me, and don't cross the mob. Don't get in the way of teenagers and sugar. Believe me, that's a bad thing.
Sounds like 1 versus 100.
Yeah. So, all right. See the list in the middle there of stuff? Which of those is the fastest thing in that list? Which of those is the fastest speed? Light. Light is the cosmic speed limit. In fact, Einstein showed that we cannot go faster than light. So, which of those is the biggest speeds on the right-hand side? What would go with light? Okay. Which of these do you think is the next fastest? I don't think it is. Don't think sound is. There's something on there that breaks the speed of sound. Yeah. I think fighter jets go more than the speed of sound. So can someone divide this by 3.6? Let's put this into meters per second so we can do a comparison. 1,000 meters per second? And the reason is, I happen to know that the speed of sound is 333 meters per second. That's actually not quite right, but it's such an easy number for me to remember. The speed of sound is around 330, but I always remember sound 333. And actually, it varies. The speed of sound changes depending on how humid the air is, how much rain there is in the air. The speed of sound changes depending on your altitude, changes depending on the temperature. That's why, for example, on a cold, clear winter day, it's not a coincidence, sound does travel further. On a muggy, humid day when it's raining, sound doesn't travel as well. It's why you can't hear traffic noises as well on those kind of days? Okay, so I know that sound is 330 meters per second, which is the top one there. So yeah, I'm pretty sure the 1,000 meters per second, which is just not quite, almost 3 times the speed of sound, I think that's the top fighter jet. So a fighter jet can go 3,600 kilometers per hour. Are there any of these other ones that, you know what? I know the one right below light. You're getting your driver's licenses. Some of you have your driver's licenses. What's the speed of a car on a city street? 50. Hey, what do you think? Let's do the one below that. From looking at what's left, what do you think a Formula One race car travels at? 220 kilometers per hour? Okay. Are there any of these other ones we can make a guess? Which of those do you think is a human walking? Yeah, I think, you know, a human walking goes about 4 kilometers per hour. What about the fastest human running? You know what? Because Usain Bolt, they roughly run 100 meters in 10 seconds. So yeah, about 10 meters per second, give or take. All right, we're down to 2 left. Fastest animal. Wait, what is the fastest land animal?
Isn't it cheetah?
Yeah.
100?
Chris?
I can't pronounce that because I don't know what they actually.
So I grew up on non-metric and I watched American nature shows. I know a cheetah travels 60 miles an hour. But wait a minute, 60 miles an hour, I've driven in the US. That's the US freeway speed, right? The Canadian freeway speed is 100 kilometers per hour. You know what? That's a cheetah. What's the terminal velocity? What do we mean by terminal velocity? Do you remember? What does that mean? When I jumped out of an airplane, I've mentioned I jumped out of an airplane, I hit terminal velocity. What is terminal velocity? So in real life, see, we've been dropping objects and we've been ignoring air resistance. In real life, once you get going really fast, just like we looked at the Penny video, we found that there's a terminal velocity. You stop accelerating at negative 9.8 because air resistance starts to slow you down. It doesn't mean you're floating up there. It means you're still coming down at a terminal fatal velocity, but your acceleration is terminated. You're not speeding up anymore. So terminal velocity for a human, I always remember around 50 meters per second, or here 55 meters per second. Just to give you an idea of what some really big and what some really small speeds are. Okay. So relative velocity, the trick is you don't look at both objects. You pretend one object is standing still and use the velocity of the other object relative to that first object. If they're coming towards each other, you'll just add them together. If they're traveling in the same direction, you'll go bigger minus smaller. Oh, and acceleration for relative velocity, Jake, is going to be 0. What's your homework? 2 things. So first of all, from here, try number 1. Try number 2. Oh, number 2 we already did. I didn't change the numbers. Okay, so you know what? I'm going to give you number 2, but I'm going to change the numbers. So let's do that still. Make the 10 meters per second a 15 meters per second. Make the 6 meters per second a 7 meters per second. And I got no idea what the answer is, but it won't be no 28.8 anymore. And then I got a few more. So you can do number 1, 2, 3, 3 is a challenge, but I like number 3, I like number 3, I like number 3, I like number 3. I haven't done one quite like that. There's an extra step you'll need to do. I'm curious to see who can put that together on their own. Otherwise, I'll talk about this next time I see you. Skip. No, 4 is good and 5 is good. Okay? And the last thing I have for you, because this won't take you all class, and also I know some of you want to get a head start, I'm going to give you your unit review. The unit review is due the day of the test. When's your test? A week from today. So give me 1 second, I'll hand that out. So looking at the unit review, come on computer. This thing here. So a couple of conversions. I'm just going to assign most of these. Let's see here. Yeah, that's good. Cross out number 4 on the unit review. Psst, cross out number 4 on the unit review. Can ignore that. Sure, 5 is okay. 6 is okay. 7 is okay. Yeah, these all work. And then we have velocity, acceleration. You can cross out number 1, number 4. Well, no, let's not cross out number 4. I take that back. Oh, fine. Hey, look at number 4. Number 4 says, under what condition can acceleration be calculated simply by dividing change in speed by change in time? If you have a constant acceleration, which is all we've looked at this year anyways. Now cross out number 4. A uniform acceleration. If acceleration is changing, it gets complicated and you need calculus. 5 is good, interpreting a graph. 6 is good. 7, we have a speed time graph. Good, 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 good. You can cross out 7E. Eight is good. 9 is good. Now 9, you've got big numbers here. These are, hey, we practiced some scientific notation. Sorry, when you're going into space, the numbers get big in a hurry. So 9 is good. Cross out 10. Cross out 11. Cross out 12. I cross out 12. Cross out 14. $15 is good. 15 is good. That's why I said 15 is good. 16 is tricky. That's tough. I'm going to let you see if you can figure that one out. Let you think about it. Cross out 17. Okay. And then the answers, I think, are attached. Then we come to an acceleration review. Yes? I hope. Yeah. And do you guys have the answers in did they show up on yours? Yeah? Okay, good. So number 1, but you can cross out E. 2 is good. 3 is good. 4 is good. 5 is good. 6 is good, but you can cross out C. You can cross out D. You can cross out E. You can cross out F. So really 6A and B, I guess I could have said.
Could you go to like the one before that?
I'll bring him up in a second. 7 is good. 8 is good. And you'll get all Monday to work on this stuff too. 9 is good. So 9, we're on the moon. When you drop something on the Earth, what's the acceleration? When you drop something on the moon, what's the acceleration? Negative 1.67. That's why stuff falls slower. That's why you feel lighter. Cross out 10. Let's do 11. 12 is good. Skip 13. Oh, sorry. Hang on. Skip 13A. I'm not going to make you do the graph. But B is good and C is good, because you can do that from the information. D is good. E is good. And the answers for that one are all next to them, yes? So that's lots of practice. If you do that, I don't think you'll find any surprises on your test. The only thing also on your test, the very last question, I'm going to give you some data, distance and time. I'm going to ask you to graph a distance and time graph, and then or a velocity time graph, and I'll ask you to tell me something about the slope, which is either going to be velocity or acceleration or something like that. Please make sure when you graph that you remember that every graph has to have a title, and you have to label the axes, and you have to have a scale, and all that stuff. I'm done.